Alright, let's talk about a slightly different behavior. We saw that initially when we played out the simulations, then the blue body stayed where it was and the red body kept moving with a constant speed covering 5 meters in each second. And the graph of this situation looked something like this. Let's change a few things about this. Let's suppose we increase one of the properties of the blue car, and this property is known as acceleration. And acceleration means that the speed of a body will change by some quantity each second. If it's a constant acceleration, then the speed of the body will change by the same amount every second. So right now it is 0, so the speed of the body will change by 0 units of speed each second. But if I take it to 0.5, let's say, then the speed of the body will change by half unit of speed each second, which would mean in the first second it will get a speed of 0.5 units, in the second unit it will become 1 unit, then 1.5, then 2, then 2.5, and so on and so forth. I would like you to take notice of the red speed and the blue speed and see if you can justify the behavior of these numbers with the behavior of these actual particles that will display the motion. Let's take a look. You can see that the red dot is performing the same behavior, which is it is trying to cover 5 meters in every second, and that is why its speed remains 5. But you saw, and I will play it again, but you saw that when the blue dot began, it was covering very tiny distances in each second. Each dot is plotted after 1 second, and you can see that the blue dot covers more and more distances in each second. The intervals between the dots are growing every second, whereas the red dot maintains the same space between the points in each second. So the red dot covers 5 meters every second, whereas if you take a look at the blue dot, the speed is changing every second. Every second, half unit of speed gets added to it, and after a period of 20 seconds, since each second adds half unit, then 20 seconds would add 10 units of speed to the speed of the blue dot. And this behavior is displayed with a slightly different kind of curve if you plot it on a graph, and I will show you the behavior. Now I will play this and you will see the behavior of the blue dot. Earlier it was just a horizontal line and the red would move in a slope form, but now let's see. You can see that the blue starts off with a horizontal behavior, but then it curves up and it speeds up, eventually catching up to the red dot, as you can see at the 20th second. So at the 20th second, both have covered the same distance, although you can see that the blue one begins with a lagging behavior. The blue one is covering less distance so far, but eventually at the end of 20 seconds it catches up to the red dot, and both have covered 100 meters at the 20 seconds. And if this time were to continue, the blue dot would speed up and it would take over the red dot, and it will start covering more distance in the same amount of time. So if this were to move to 25 seconds, then the distance covered by the blue dot would be greater than that of the red ball. You could see that that if I had allowed the blue dot to move any further, then it would have taken over the red dot with the pace and with the trend that it is going. You could actually see that if I could increase the acceleration to a higher number. Let's take it to 1 unit every second. Now the speed of the blue dot will increase 1 unit every second. Let's see how that plays out. So each second its speed will become 1, and the next second it will become 2. So now you can expect that in 20 seconds the blue dot will reach 20 units of speed, because each second it will get added with 1 unit. So acceleration of 1 unit means each second 1 unit speed would be added to its speed. So let's see. Now you can see that it again begins with a slower speed, but you can see that each second the speed is growing and it takes over the red ball, and in the same time, so in 14.15 seconds, it covers more distance as compared to the red one. And you can clearly see that when things are speeding up, then their behavior can no longer be displayed with a straight line if position and time are in consideration. So let's go to the Desmos and see if we have a way of regenerating this behavior. I'll hide the previous graphs, and now I will try to draw a position versus time graph. It's a position versus time graph that depends upon some constant, let's call it a x to the square. The argument is t, so I should write t here. Okay, now you can see that this is somewhat similar to this curving behavior, but it is a lot steeper. So if I slide this a backwards, so I can somehow some sort of similarity can be obtained by tweaking the value of the multiple with t square. The basic equation is this. It is the general form to sort of get at least to the template of the behavior that it is being displayed by the blue dot, and to get closer and closer to our behavior, you should have a knob here that is getting multiplied with t square, and if you decrease it to some value here, then you sort of can approach the value. So I will go with from 0 to 2 and 0 to 2, and the step that I want here is 0.01. So now I would be able to in a lot better position to sort of match the behavior of the car, the blue dot, and to make things a bit easier here, I will go back and see that let's say in what was our previous example? Our previous behavior was this. Maybe this has some easy data points, so I'll play this out and I'll choose one data point and I'll draw that figure out. So you can see that maybe I can take let's say this point. I can take that in this behavior at the 18th second, at the 20th second it would pass through 100 meter mark. So you can see that at the 20th second. So for this to pass through 100 at the 20th second, I will have to tweak it in a certain way. So you can see that right now at 20 it is passing through 28. So I will have to raise this constant to a certain value that at 20 it passes through 100. In 20 seconds it should have changed its position to 100. So still not there, and I'm changing this A, and now I will move even further. We are still not at 100. I'll tweak it a bit more, and let's see that in 20 seconds we have exceeded the mark. So I'll go back a little, and now at A equals to 0.25, you see that we have achieved that situation that at 20 seconds, after 20 seconds, the body would have covered 100-meter mark of position. And you can see that is the case, that in 20 seconds this body has, the blue body has covered, in 20 seconds it has covered 100-meter mark. And this behavior, as you can see, I have successfully drawn it with this position versus time equation, where A should have the value of 0.25. So this is one more example of how a complex behavior can simply be put in the form of a graph, and even simpler in the form of an equation. All that matters is that you should get to the right constant to exactly reflect the situation that is under consideration. And let's see what this 0.25 means in this situation. Let's see what it means, and if it actually if this behavior actually reflects our behavior. So this behavior shows that do we have any other point where we could check this? Let's see. So at 10 this shows something lower than 40. So it's somewhere between 0 and it's somewhere above 20, right? So let's see if our behavior is correct. So at 10 it is somewhere above 20, but this shows exactly 25, and this one doesn't really show 25, because if this is 25, so this is tricky. So what I'm trying to guess at here is that what does this 0.25 number mean in our context? Why do we have a 0.25 over here? What does it mean? And that is a question that is to be answered, but I cannot answer it as of yet. But can you see that 0.25 and 0.5 have a relation of half to whole? And I will shed some light on this later on, but the key idea is that you have observed a bit more sophisticated behavior which you have plotted on Desmos as well, and you know that you need to add a square to the independent variable to get such a behavior.